So we now move on to the third part of the chapter, work, power, energy, that is conservation of energy. Yeah, we know and we've been studying since it is 3 years, in 7th or maybe 6th, that energy can neither be created nor can be destroyed. It can be just transformed from one form to another form. So this is now, in this particular chapter, you are going to see that how the transfer of energy, that is from potential energy, the thing gets converted into kinetic energy, and how the total energy of a body is going to remain the same throughout the travel. So according to the principle of conservation of energy, energy can neither be created nor can it be destroyed. It only changes from one form to another. In universe, energy occurs in various forms. The sum of all forms of energy in the universe remains constant. So that's what they say, that what was the energy millions of years ago and what is the energy presently, it has been the same throughout. It has never changed. It has always been constant. That means only thing what has changed is that initially it was in the form of a chemical energy which is now converted to heat energy, or something which was in the form of a light energy getting converted to some energy, other kind of energy. So it has just been transformed from one form of energy to another, but energy is neither created nor it is being destroyed. So when there is a transformation of energy from one form to another, the total energy always remains same. Okay, so it is always that the total energy which is going to be there is always going to remain the same. It remains conserved. If there is only an interchange between the potential energy, kinetic energy, the total mechanical energy, that will be the sum of the kinetic energy and the potential energy, remains constant. So we have over here that K, that is the kinetic energy, plus the potential energy will always be constant. So that is K plus U is going to be constant where there are no frictional forces. So we are not considering any loss of energy due to energy degradation over here. We are just considering that if there is a pure formation or pure transformation of the kinetic energy into potential or potential to kinetic, then it will be such that there will be that sum of kinetic plus potential will always be constant. So the principle of conservation of energy is one of the fundamental principles of nature. So we know very well over here. Now we need not go through what is written over here. We'll exactly do it over here on. We are going to prove that how come the total energy of a body which is freely falling is going to be constant. So we have the first thing as, suppose there is a body over here. So there is a ball over here. This ball is at a location which is at a distance. So this is the ground level over here. So this is the ground, and this is at a distance of, let's say it is h over here. Okay, so this is point A. We take in the middle somewhere a point B. So this will be the point B over here, which is at a distance of x from here. So accordingly, this distance over here remaining over here, which will be x minus h minus x, right? So the body is freely falling over here, reaching this point at the end. This is point C. Okay, so we got three things. The first one is the body A, which is here. We are going to check what will be the condition of the body at point B, which is at somewhere x, after traveling x meters from the top, and then finally when it reaches the ground at point C, what will be the value of the energy present in that body. Okay, so let's see one by one. The first condition, at this particular point, what is happening? body is like this. The body is over here like this. Okay. What does it have? What does it have? Potential energy, right? So what is the potential energy over here? The potential will be equal to mgh. So we have over here at point A. So initially the initial velocity is 0. We don't want to find out the velocity at the initial velocity is 0, what I know. So we know over here the u is equals to mgh. K will be equal to half mu square, which is 0 because u is 0. It's at rest. It is stationary. Therefore, K plus u will be equal to 0 plus mgh is equals to mgh. So what is the energy at this point? At this point, it is mgh, right? Or we can write it in a proper manner. We can say K is equals to 0, u is equals to mgh. Now we move on to some point number B. Point number B over here. What happened? Here it is already traveled, so it is traveling over here with a velocity v, right? So K will not be 0, it will be K is equals to half mv square, and u will be equal to mg h minus x, because that is the distance between this point and this point. This is x is already traveled, which is h minus x, right? So we see over here that at point B, my u will be equal to, so my u will be equal to mg h minus x, and my k will be equal to half mv square. Now over here you can see here that v, my v over here, I want to find out the v over here. It has already traveled a distance of x, which is already known to us that the distance traveled by it is x. So we are going to use the equation of motion, that is v square is equals to u square plus 2as. Now over here, because it is x due to gravity, therefore v square, u square is 0 square plus 2gh, because not h, it will be x. Understood? The distance traveled by it is x. Acceleration due to gravity is g. U initially was 0, v we want to find out. K is half mv square, so k is equals to half into m into v square is nothing but 2gx. So 2 gets cancelled, so it is nothing but mgx. So k plus u will be equal to mg, this is nothing but mgh minus mgx plus, sorry, k pehle likhna hai, so it is mgx plus mgh minus mgx cancels, so it is equals to mgh, accordingly same as what was earlier. Samjha? What we did was simple application of the equations of motion. What is the equation of motion? V square is equal to u square plus 2as, where a is the acceleration. Here it is a freely falling body. Freely falling body. Acceleration due to क्या होता है? Gravity. G. It is traveling. So it traveled from here to here. So this distance is x. So s is x. Accordingly, half mv square will be equal to half into v square is 2gh, gx, so it is 2gh, 2 to cancel, mgx. mgh minus x So it is mgh minus mgx. So mgx cancels, you get mgh. So at point B, we saw that it comes out to be total as mgx. Right? Now let's see the last point, that is point C, when it is just about to touch the ground. When about to touch the ground, at that time, what is the velocity? That's fine. Now we know that here u is going to be mgh, where h is now 0 because it has reached the ground. So u will become 0. So we point C, u is equals to 0. Since h is equals to 0. Take the same equation. V square is equals to u square plus 2gh. As के लिए gh ही ले directly. U is 0 because it was 0. So equals to 0 plus 2 into g into the total distance traveled is h. Yes, it is h. So it will remain v square is equals to 2gh. Therefore, k is equals to half into m into 2gh. 2 gets cancelled, is equals to mgh. Therefore, k plus u is equals to z. It will be mgh plus 0 is equals to mgh. So you can see that all these three cases, the total energy. So here k will be equal to mgh, and hence the total is equals to mgh. Here the total was mgh. Here the total is mgh. Also here the total is mgh. So you can see this is a very, very, very important proof over here, because without, you need to learn this thing by heart. It's normally a 4-mark question. That's right. Yeah, this is a very, very important proof. It is asked as a 4-mark question, or sometimes less, maybe 3 marks, but not less than that. It is a question which is come many times in prelims, in boards, and you need to prove that when a freely falling body, the total energy, the sum of the kinetic energy and potential energy remains constant. So for that, you have to start with this diagram, write this x and h and everything, and then you need to prove this thing, saying that point A, it is mgh, point B, it is mgh, and point C is also mgh. Accordingly, we prove that by the conservation of energy. So this is a very, very important part. It is already given properly even in the textbook, so you can go through that also properly. So yeah, it's very, 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 very important. So the same thing would also happen when it is thrown upwards. If a ball is thrown upwards, exactly the same thing is going to happen over here. So the points and everything will remain the same. So there is no change in the proof whether it is a freely falling body or it is a body which is thrown vertically upwards. So when the body is going to reach the highest point, at that time your kinetic energy will become 0 and your potential will become maximum. So at the start, the kinetic energy will be maximum, and then as you go through, when you are thrown it upwards, so you are thrown it upwards, so kinetic energy is going on decreasing because the gravitational force is acting on it. So kinetic energy goes on decreasing, becomes mgh के बाद में it becomes mg, this will be your mgx, and then it goes to and reaches here. When it stops at that particular height, my kinetic energy will become 0, but the potential energy will become mgh. So this is exactly the same whether you throw it upwards or you are throwing it vertically downwards. So in both the cases or at any instant. So what we prove over here, we are not proving it only at the halfway point, it is at any point. That's why we are taking the x. So at any point when a body is freely falling or a body is thrown vertically upwards, the sum of the kinetic energy and the potential energy is always going to remain constant. So that's what they have also given as a tabulation, that if it is a downward motion, then in that case the kinetic energy initially over here at the highest point will be 0, when it is downward motion. When it is downward motion, then the highest point, the kinetic energy is 0 and potential energy is maximum mgh. At halfway point, the both will be half mgh, half mgh, both the cases. And at ground level, my kinetic energy become maximum mgh and the potential becomes 0. Whereas when it is upward motion, at that time my kinetic energy from the ground, so kinetic energy is maximum, that is mgh. At middle position, both are half mv square, half mgh, half mgh. And when it is at a height a, that is when it reaches the top, at that time kinetic energy becomes 0, potential becomes maximum. So this is what they are given over here, and accordingly they have also given you a graph regarding this, and this graph is very, very, again it's important. Many times they make a question regarding this thing, so identify that which graph is kinetic energy, showing the kinetic energy, and which shows the potential energy. So you have got over here, this is the height over here, this is the height. So the height is increasing over here, so it is going to go on increasing over here height wise. And this is the energy, this is the energy. So you can see, so if I'm having a body which is going to be if a line is like this, okay, let's take it this way. If it is like this, what do you understand? If this is potential energy, suppose this is potential energy. So what do you understand by this line? That the energy is keeping on increasing. Why would it keep on increasing? When would it keep on increasing? When it is thrown vertically upwards. So when it is vertically upwards, then it is going to be like this. And if there is a line like this, that is kinetic energy coming like this, at that time, this is kinetic energy. So when it will be dropping down, yeah, when it is thrown vertically upwards. So so you can see this graph where potential is like this and kinetic is like this is for upward motion. Okay, so that is the motion against the gravity. Okay, the conservation of mechanical energy, that will always be seen that kinetic energy and potential energy are going to be this way, that one is falling downwards, other is getting upwards. So this is how we are going to represent this thing. So we have the note, the initial kinetic energy provided to the body at the ground so as to reach a certain height h must be equal to the potential energy of the body at that height, that is equal to mgh. Thus the initial velocity u to be imparted to the body so as to reach the height h is given as half mu square is equal to mgh, or u square. So half mv square is equal to mgh is what we needed. Hence u, initial velocity, will be root of 2gh. So anyway, you won't require it because normally you will be solving the sums using this thing, so not required. Now the figure 2.18 represents the variation of kinetic energy and potential energy with the height above the ground. The table below represents the kinetic energy, potential energy, and the total energy E of the mass. So yeah, this is what they are given here. So it's quite an easy thing. Now we very well know over here that potential energy keeps on increasing and kinetic energy keeps on decreasing. If this is potential energy and this is kinetic energy, then it is freely falling. Means when the body is, so initially the body has got higher energy and it is going down. तो क्या होगा? Freely falling body. When the body has got more potential energy and the potential energy is keeping on decreasing, like in this case, the potential energy keeps on decreasing, kinetic energy keeps on increasing. So this is upward motion. वही उल्टा होगा. Now suppose if it is this way, that this is potential and this is kinetic, then what happens? It is, the green one will be downward motion. So when the motion is upward, it is the red color thing. That potential energy upward में क्या होगा? पहले kinetic energy दिया है, so kinetic energy maximum and potential energy minimum. As it goes up and up and up, height goes on increasing, potential energy keeps on increasing. Right? As my height increases, potential energy keeps on increasing. As the height increases, the kinetic energy keeps on decreasing. In the green one, which is, this is potential energy, this is kinetic energy. Potential energy in the green one, that is downward motion, पहले potential energy ज़्यादा है, it is keeping on decreasing. And at that time, kinetic energy is 0. When it is up at this point, kinetic energy is 0. When it is falling down, the kinetic energy is keeping on increasing. Got it? So this is how you can identify whether the graph is for vertically upward motion or downward motion. Now, there's a certain note which is given over here along with the for the calculation. In the above calculation, we have ignored the force of friction between the body and air. In fact, during the fall, some of the kinetic energy will change into heat energy due to friction, and it will get dissipated in air. At the ground C, the kinetic energy will be less than mgh. The conservation of the mechanical energy is therefore strictly valid only in absence of external forces such as friction due to air, etc. Although the total energy, all kinds, is always conserved. So yeah, the total energy will be conserved, but yeah, whenever there will be a body which is going to come freely falling like this, at that time we cannot avoid the friction of the body with the air, the buoyant force. We cannot avoid that, and due to that particular buoyant force of friction, when the body reaches the ground, at that time it may not have the exact mgh of kinetic energy. It will be slightly less than that, because that much amount of energy will be used up as frictional energy, and which may be converted into heat energy. So no doubt the total energy, that is kinetic energy plus the heat energy generated due to friction, that will be equal to the mechanical energy. The total energy, that constant will be there, because potential energy gets converted to kinetic, and then kinetic get converted to heat, and also automatically the total energy will be the same because it is going to be conserved. But only thing is that it will be a degradation of the energy, because it was an unrequired change which took place when it was falling downwards. Now the same application or the same principle can also be applied on a pendulum. So if you have got a pendulum, then pendulum also gives you the same kind of the application as the freely falling body. So if this is the rigid support to which there is a pendulum which is connected like this, and these are the two extremes of the pendulum. So we have the pendulum as extreme 1 and 2. So if we see, this is point A and this is point B, this is point, again this will be C over here. So if this is the condition, what will happen at this particular point, right? It is at rest, ground level. So what will be the potential energy? U will be equal to 0, but you are going to give it a push. When you give it a push, what will happen? This is going to move this way. So you have given kinetic energy over here, and that kinetic energy will be equal to the potential energy what will be getting here. At this particular point, what will happen? The velocity is going to stop, the ball is going to stop, because it is going to go here, stop here, and then come here. So when it stops, velocity becomes 0, means kinetic energy becomes 0. But potential energy will be equal to mgh, because that is the height to which this has travelled upwards. So this is the height. So it has got to this particular height to which it is going to get. So this is mgh. Over here, this will be mgh again. And at this particular point, again, when it is moving this way, at this point, k will be equal to 0, but u will be equal to mgh. So you can see, if I start the pendulum with taking this over here and releasing it, so at this point, when I release it, my potential energy was maximum, goes on decreasing. At this point, potential energy is 0, but kinetic energy maximum. So that kinetic energy will push it over here. When it reaches here, kinetic energy keeps on decreasing, but the potential becomes maximum. At this point again, it will stop and it will have more potential energy, less kinetic, 0 kinetic. So again it will come down. So while coming down, potential decreases, kinetic increases, kinetic again becomes maximum. And instead of stopping, it keeps on going here, and so on. So you can see that once the pendulum is set into motion, it will never stop. It will be continuously moving to and fro without stopping. But what is the condition? No friction of air. Okay. So if there is no friction due to air, this will continue to travel like this. Okay, it will keep on doing like this, because there is no loss of energy. The loss of energy is there only if we take friction into consideration, friction of air into consideration. Only then it would happen that this will slowly damp and become zero. So that's why we see that any point over here towards the swinging. So during the swinging, during the swing at the extreme position B and C, the bob has only potential energy, where the mean position A, it has only the kinetic energy. So at here, this particular point, it has got only kinetic energy, whereas at the two extreme points, it has got the potential energy. Yeah. So at an intermediate position between A and B, or between A and C, the bob has both kinetic and potential energy, and both, but the sum of both will be total mechanical energy, which is going to remain constant throughout the swing. This is strictly true only in vacuum, where there is no force of friction due to air. So this is the most important part, that this is possible only in vacuum. Without vacuum, you cannot have this particular kind of a movement of the pendulum continuously going on from to and fro. So that was the explanation about the chapter. A very important part of the chapter was that the proof, or we can say the derivation of the kinetic energy and potential energy remaining, the sum of these kinetic and potential energy remaining constant for a freely falling body or a body thrown vertically upwards. So I think I'll better stop over here and do the numericals in the next lecture.